So last time, right, we were here somewhere here that on the enamine hydrolysis. Anyways, I asked that we'll be doing problems, right?
Yes, I did all the problems from the previous chapters. Yeah.
You have not sent me what?
Yeah, sir. I'll send it now.
Yeah, okay. You can send me now. And it's better that what you do is that you make a PDF using Adobe Scanner and then send me, okay?
Okay, yeah, yes, sir.
Because that is always helpful, and it'll be good for you also, right?
Yeah.
When you're able to see. Anyways, you did these 32, 33.
So these ones I couldn't find, but I did the previous ones. 62,
Okay, no problem,
63,
no problem.
79.
Do these,
Yeah.
okay. Don't write the mechanism, write the products for 33.
Yeah.
Okay. What are they teaching in school now?
So they're doing alcohol phenol ether.
Okay. Just add more notes for you. Yeah, I've got it. Aldehyde.
Yes, sir, done.
Okay, send me.
So I'll send it as a PDF, right?
Right now, for these, you can send me just like that, and later on,
Yeah.
And did you take care of the cis and trans EZ or forgot?
Oh, okay. Yeah, I'll do that. Yeah, yes.
No problem, no problem. That is not easy, yeah. When we went to IT, in IT we were forgetting.
So for 33, right? Cis and trans?
Yeah, yeah. For 33, we'll get in some cases we'll get cis and trans, right? We might
Yeah.
get, right? I think we'll
Yeah.
get in C and D. I think we'll get.
Yeah,
Right.
yes, sir. C and
No.
D.
Huh? Right?
Yeah. So for D, how will we get? For D, I'm not getting any.
Is it of, okay, 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 okay. We might not get for this. Yeah. I'm just saying you have to check.
Yeah.
Check in which case we are getting and which case we are not getting. Um,
So I'm getting only for C.
in the case of cyclohexyl, I mean, you will have acetophenone, right?
Yeah.
N, right? It's a lone pair, right?
Oh, okay, yeah.
Now you understand what I'm saying?
Yeah, yes, I got it.
Okay.
Okay, yeah, yes, I drew the structure of cyclohexylamine down.
No problem, no problem. It's a cyclohexane ring with NH2. Huh?
Yeah, I drawn N as a part
I
of it.
got it, got it, got it, I got it. So do the nomenclature questions also, Neha. Okay?
Yeah, yes, sir.
Okay. We just don't want that we should do some things incorrectly just because we don't know the name. Got more
Yeah,
books.
yes, and now I'm getting cis and trans for C and D.
So C you will get and D also you will get,
Yeah.
right? Send it and then we'll go.
Yeah, yes, sir, sent.
Let me check. Okay. 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 1 second. So, hmm. You don't have to write cis and trans, but you have to draw them like that. Okay? Because
Yeah,
they
I
won't
got
be
it.
cis and trans, they'll be E and Z.
Yeah.
Got it?
Yes, I got it.
So just draw when and yeah, just switch the lone pairs and okay, nice. Okay, reductive amination. This is a very fancy, nice way to make amine. See, what we do is we treat it with ammonia and we'll get this. And this is unstable, and immediately we add H2 palladium to it. HH is added, we get amine. H2 and see, this is what we are doing. Huh?
So why is that unstable?
This is unstable because you are not, we are not able to isolate it in the lab. I don't know why it is really unstable. Okay. But I think there, suppose if I get and if it gets protonated, then what will happen, right? Will it be reversible? That is, I think, what we have to say. I think this is pretty reversible. I think that is why it is a single hydrogen atoms. Yeah, that is quite labile. I mean, it is going back. That is what they're saying actually. It immediately it is because the water will be like this, and so I think in this particular case it is coming back and getting here, right? That is what they're saying. Okay. So this is relatively unstable. So anyways, what we do is we immediately reduce it. Okay. And we get this amine, and this is a very nice way to produce amine. It's very important way also. Okay. Clear?
Yes, sir. Yeah.
Okay. Yeah, yeah. I really have no idea why it is relatively unstable. Why it should be. But I think it is relatively unstable because it does not have any alkyl group, and hydrogen is pretty. What we call, the word we use is labile. It'll immediately come back, and I think it'll react. I'll check it out. Huh? No worries. But the main idea is that we'll get something which is called imine. This, and immediately we add H2, and then we get a primary amine. This is a very nice way to produce a primary amine. Okay, that is the main thing. Okay. And sometimes we use this sodium NaBH3CN, sodium cyanoborohydride is used. Okay. And again, why it is stable even in acidic conditions. Okay. See, NaBH3CN is differing from this because it has a CN group in place of one of the hydrogen. Okay. So yeah, this is the another reagent. I don't know if you have it in the NCRT or not, but you can check. Okay. See, the same thing is happening here. Imine is relatively stable. Okay. Right? This is clear, right?
Yeah, so yeah, just going through it.
Yeah, yeah, just go through it. You will get it. The same thing we'll get, and then we'll reduce it.
Okay, yeah, so everything in the last step I just
Yeah,
added.
yeah, yeah, yeah.
Yeah. Okay, yeah, yes, I got it.
Right. See, same thing is happening, huh? We are just reducing it, huh? Double bond is getting reduced, huh? Okay. I mean, okay. See, enamine is in resonance, huh?
Oh, okay, yeah, sir. So then if it's in resonance, why are we shifting that? Because won't the resonance be more stable?
This is a plus and this is minus, huh? Okay, this is something like this, huh? When the acidic medium, this will get this, and then I can add H negative here, huh?
Yeah.
Okay. When I draw the lone pair and shift like this will get negative. This can get the proton from the trace acid, and then from H negative we can. Got it?
Yes, I got it.
Okay. Okay. Now, 34, do homework. 35 also do. See, you can sense a certain cyanohydrins here, right? Or we can start with the alpha aminocarboxylic acid with the, if you want to start with the carbonyl compounds, right? You see, we have to imagine the reverse.
Yeah.
So just before that, we can imagine that this is a carbonyl compound and then we oxidize it. Okay.
Yeah, okay, yeah,
Just
got it.
yeah.
Yes.
Just do it. You can get. And okay, we don't want this for the moment. Okay. Now again with the water, see what is happening. Uh, H2O is added, and again this is not very stable. Whenever carbon has two heteroatoms, two oxygens or two nitrogen, it will immediately lose water. So you can see that it is in equilibrium first of all. Okay.
Yeah.
So a little bit of hydrate always exists whenever we have aldehyde or ketone and moisture, right? It will add because it can act as nucleophile and we'll get a gem diol. Gem diol means there are OH groups on the same carbon. Gem means on the same carbon. Okay, and you can look at the mechanism. You just look at the mechanism. I'll bring water. The same simple mechanism, right? Okay, I'll bring water just. Yeah, this is clear,
Yes, sir, clear, got it. So
right?
in this last step, how are two OH existing in the same carbon? Because isn't that unstable?
Everything is in equilibrium, huh? Okay. And the equilibrium was
Yeah.
on the left side, huh? Okay.
Yeah,
Got it?
got it.
Okay. Well, I think she must have has discussed equilibrium. So yeah. See how much aldehyde or ketone is hydrated. See what is happening. The moment starting, we'll start from this. The formaldehyde. Okay. This will start with. So obviously we do not have any electron donating groups here. So carbon delta plus is maximum here, huh? Right? And now this methyl group is so it is destroying the positive, huh? Yes.
Yes, sir, yeah, got it.
So the maximum is hydrate is on the bottom. Also, one more factor, Neha, is these are electronic factors, and you see after the formation of hydrate, this carbon has become sp3 hybridized, right?
Yeah,
So there'll be most steric repulsion will occur in the first case, right? Because it has two alkyl groups, huh?
yeah, yes, sir, got it.
Got it? OH, right? So see, these will repel. But in the other case, we'll have only methyl and hydrogen, and here we'll have the least repulsion, right?
Yeah,
There won't be any repulsion. And I think there are more cases of this. So this is how it is, okay? Same thing what I'm saying. First of all, the electron donating groups are going to make a carbonyl compound more stable, right? Delta plus will destroy it. So it will be less reactive, right?
yeah,
Right. neutral species are always more stable than the charge. Since oxygen is producing a positive here, so these are helping it to stabilize. Okay, right?
Yeah, yes, I got it. Yeah, got it. Yeah.
Okay. Let me know whenever you don't understand, please. Okay.
No, sir, clear.
Now, and again, this is the same thing which I just told you that they have become sp3 hybridized, so it'll be most repulsion here, right? Same thing. Okay. Bond angles have gone from 120 degree to 109.5 degree, right? So repulsion is most in the case of ketone, right? In the first.
Yeah. Yes, sir,
Okay.
I got it.
So electron withdrawing groups are going to increase the hydrate formation. Huh?
Oh, okay, yeah.
Because electron withdrawing group are going to, so electron donating substituents and with the bulky substituent decrease the percentage, and electron withdrawing substituent and small substituent increase the percentage of hydrate. Okay,
Yeah.
so which ketone is going to form more hydrate, A or B?
Uh, so B.
Yes, right. This is a very nice thing. See, when trichloroacetaldehyde is dissolved in water, almost all of it is converted into hydrate. Oh my god. Huh? And the product is chloral hydrate, or the it is a sedative that can be lethal. Okay. Okay.
Yeah.
A cocktail laced with it is known as in detective novels, because she reads detective novels. Huh? I told you, right?
Yeah.
In detective novels, at least, as a Mickey Finn. Okay. So explain why an aqueous solution of trichloroacetaldehyde is almost all hydrate.
Yeah, so that Ci will take the electrons.
Yeah, of course. But why not in the above problem? Why it is almost all the hydrate?
Oh.
Maybe it has got something to do with the hydrogen bonding.
Oh, okay, yeah.
Huh? Right?
Yeah, yes, I got it.
You can see, huh? Right. What is happening is, but the hydrogen bonding, you see, normally we know that it is formed with fluorine, oxygen, nitrogen, right? Something like that, right? Oh,
Yeah, yes, I got it.
no, let me draw. So in this particular case, it will look something like this. Huh? C, Cl, Cl, Cl. Because these chlorine are also what you call,
Electronegative, yeah.
right? OH. So although it is not found with the specifically with the chlorine, the hydrogen bonding is not found, but here it is because there are so many chlorines and they are withdrawing, so the chlorines are getting a sufficient positive charge. So that is why this hydrogen bonding is going to exist. Okay, something like this. Okay, this is how it is going to exist. Got it?
Yes, I got it.
Okay, so that is how it works. Okay, so great. And preserving biological specimens, formalin. Okay, so 37% solution of formaldehyde in water known as formalin was commonly used to preserve biological specimen. It is an eye and skin irritant, so formalin has been replaced with other. Now another is 2 to 5% phenol. Okay, proving that the hydrate is formed. Okay, now this is how do we know that hydrate is formed? See, initially we start with a ketone in which oxygen is not isotopically labeled. Huh?
Okay, yeah.
Okay. Now we treat it with water, which is in which water, the oxygen of the water is isotopically labeled.
Isotope,
Okay.
yeah, 18.
Okay. Now see how it is. Now if the mechanism will go on, go on, go on, go on, go on. Then finally we are going to isolate also a ketone, since everything is in equilibrium, in which the oxygen has been isotopically labeled. Okay, just
Yeah.
go through this mechanism.
Okay, yeah, yes, I got it.
Yeah, right?
Yeah.
What a nice way, huh,
Yeah.
to prove, right? See? Because if the hydrate formation won't occur, the oxygen will never be labeled, right? Right?
Yeah, yes, I got it.
If the hydrate is never formed, then the switching will never occur, right?
Yeah.
Now reactions with alcohol. Now again they react with alcohol. You see, in the alcohol, how the we are going to form the products. First, this first step is very simple, right? Nucleophilic addition, right? Because first the initially the protonation occurs and then this attacks and this opens up. Huh? Nucleophilic addition. See here. First step. Okay. Whenever there is acid, first it will protonate the oxygen, right?
Yeah.
Okay. Right. And then nucleophilic addition has taken place till here.
Yeah.
Okay. This is nucleophilic addition, right? This nucleophile is coming here. Okay.
Yeah, yes, I got it.
So till here it is clear. And after that, what happens? Again, this OH molecule is protonated, this goes out, and then further it attacks. But anyways, here comes when we have to react, when we have to get the products for 2 moles. R1, C double bond O, R2, and HOR3. Huh?
Yeah.
HOR3, right? Yeah. You know what I'm doing now?
Yes, I will remove the
So
water.
oxygen and nitrogen, we are taking out the waters, huh?
Yeah.
And supplying it to Bangalore, huh?
Yeah.
Okay, OR3, OR3, right? And R1 and R. I'm just showing you the fast way to write product. Huh? Got it?
Yes, I got it.
Fast way to write product. And the first you can write, if it only 1 mole is added, then we can immediately show the product, right? 1 mole is nothing, right? Simple nucleophilic addition, huh?
Yeah.
Right? This is simple, huh? Till here. When 1 mole of alcohol is added, 1 molecule, then we call it hemiacetal. Okay. When 2 alcohol molecules are added, we call it acetal. Okay. It's just a name. Don't try to think. Huh? Okay. Hello? Can you hear me? Can you hear me now? Okay, I'm waiting. Can you hear me? Hello? Hello? Yeah. Okay, I think. Anyways, I'm waiting. Can you hear me now? No, you cannot.
Yeah, sir, I can hear now before the current in my house and
What happened? What happened?
so the current went.
Yeah, I thought so. Yeah. I thought my power will flip, but yours flipped. See, because in the morning also it happened in my class, twice. So because there's something going on in Bangalore, some areas are hit and something like that.
Yeah, so yeah, from morning power is going and coming here.
Yeah, yeah, yeah. The 21st and 22nd there was a news. In the morning classes got hit, and then I thought evening might we get a flip, but it happened on your end. Anyway, so when we have to draw the product for one molecule, then it is clear, right? When
So I
one
think I.
molecule of alcohol is added, then we call it hemiacetal.
Okay,
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 hemi
yeah.
means half. Okay, hemisphere, right?
So only when one molecule is added, it's.
Yeah, yeah. Only when one molecule of alcohol has been added, it is called hemiacetal. And when two molecules of alcohol has been added, then we call it an acetal. Okay.
Yeah.
Now acetal we call it when it is aldehyde. When it is uh, ketone, then we call it hemiketal and ketal. Okay.
Yeah.
Okay. This is just okay. Got it.
Yes, I got it.
Hemi is the Greek word for half, right? So India is hemi brand.
Yeah.
Okay. Yes. Anyways, so I showed you how to draw this shortcut, and I'll show you some fancy products. Again, there's the same thing there. See, we are able to, since the reaction is reversible, when I hydrolyze it, I am going to get back the ketone and the two molecules of alcohol. Okay.
Okay, yeah, yes, sir.
Okay. And how do we draw the product? We simply cut it from here and HH here and OH here. So when I give OH here, I'll get something like this, and I know immediately to
Yeah,
lose
that
water
can
and
be
ketone.
ketone. Yeah.
Okay, got
Yeah,
it?
yes, I got it.
Okay. Okie dokie. So why are they stable in basic solution? So in basic solutions, the CH3O group cannot be protonated and we cannot convert it into a good living group. Huh? So you can do this as a homework, although it is solved only. Okay, and summary of the reactions. This is a summary of the reaction. So whenever we have oxygen and nitrogen nucleophile, we are focused on taking out the water. Okay, okay,
Yeah.
okay. I thought you were gone again.
No,
Okay.
no, yeah.
So now protecting groups. See what is happening here now. It's a very fancy thing. See, instead of adding two separate alcohols, we get an alcohol in which two OH are present on the same thing. In one molecule, I have two OH. Okay.
Okay, yeah.
And see how the product is going to be formed. It'll be like this: double bond of, and see OH, right?
Yeah.
And we'll take the water,
Water out, yeah.
and we'll get this, okay?
Oh, okay, yeah.
See, okay,
Yeah, yes, I got it.
right? This is, and the same in the down, okay?
Yeah,
Because
yes, I got it.
got it, right? Same thing.
Yeah.
Okay. Now these are protecting groups, and we'll see how they'll act as protecting groups. Now suppose we have to do this reduction, okay? Now I know that esters can only be reduced by strong reducing agents such as lithium aluminum hydride. Okay. Okay.
Yeah.
But if I use lithium aluminum hydride, then carbonyl group will also get reduced. But in the product, I do not want carbonyl to be reduced.
Yeah.
See, you got the problem? You understand the problem now, right?
Yes, sir. Yeah, I got it.
Because if I just use lithium aluminum hydride, then the keto group will also get
Keto
reduced
group
and
will
I
also
will
be
get an
reduced.
OH here, right?
Yeah.
So, but we don't want that. We want it to be intact. So see what we do. Initially, we first treat this with this. Okay. and it will become this. Huh? Huh?
Yeah.
Now the keto group is hidden. It is
Yeah.
ether, right? Now lithium aluminum hydride can only react here, huh?
Yeah, yeah, sir.
And then we acidify it, and when we acidify it, this also opens back, right?
Yeah, it becomes ketone again. Yeah.
Right? Nice, na?
Yeah, yeah, sir.
See, these are protecting one, right? Okay, good, cool. Oh, okay, protecting an OH group. I don't think so. This is in the syllabus, but sometimes you'll see. Hmm. Okay, maybe in the second reading we'll come to this. Huh? Okay. Or yeah, this will come later. Okay, because it's I don't think so. It is in the syllabus, although I want to teach it, but yeah. Second round, huh?
Yeah.
During revision, or you can check it out at home. Okay. See, in this case, they're basically protecting the alcohol group by using this. Just leave it for the meantime. Now, you see, the other thing which is of our business is that OH group of carboxylic acid can be protected by converting the carboxylic acid into ester. See, now this, for example, this is here. First, we make an ester. Then, when I treat it with SOCl2, only this OH group alcohol will react and will give me Cl, right?
Yeah.
Then I can use that CN and then I can open it back. See, when I have opened it back, CN become acid and this also become acid, right? Because CN is hydrolyzed to COH in presence of H plus and
H
H2O,
plus H2O. Yeah.
right? So this is it. If the acid group is not protected, then we'll get COCl and there and COH. Anyways, you can do the homeworks and what is the in a six-step synthesis, what is the yield of the target molecule if each of the following reaction gives an 80%? So if each is giving 80%, then it is 0.80 to the power 6. See how fast the yield is decreasing. Huh? Because after in the first step we are going to get 0.80, then in the second step we are going to get 0.80 or 80% of 0.80, right?
Yeah.
Or 0.8 square. Then in the third step we are going to get 80% of 0.8 square, which will be 0.8 cube, right? And in six steps, this will be the yield, which will be quite less than 100%. Huh? Let us calculate. Tell me how much is this number? Because I do not have my phone anymore.
Yeah. Yeah. It's coming as 0.262.
See, only 26%. And now imagine if we have a 40 step synthesis. Huh?
Okay, yeah, the yield will be much lesser.
Yeah, that is the problem. But Mother Nature is doing everything 100% efficiently. How can we prepare these compounds? Don't do this because we need to protect this, but this I think you can do. See here, from bromine, we have to convert it into CN, right? That is, try C, think.
So for protecting group, it can be any diol, right?
Yes, yes, yes. Yeah, yeah. But it helps if we get a 6 or 5 membered ring. Huh?
Okay, yeah.
So either we take this 1 to 10 diol, we can is a good.
Then just oxidize the Br, right?
How? There's a carbon being added. How we will do that?
Oh, okay, yeah.
So we might make Grignard and treat it with carboxylic acid.
Carboxylic acid, yeah.
Sorry, CO2, sorry. And then we get the carboxylic acid, right? Because Grignard
Oh, yeah,
reagent
if we
when
add
treated with, right?
Mgn
Remember, right?
diether, then we'll get Gringard, yeah.
Right? When we treat Grignard with CO2, we get carboxylic acid NH.
Carboxylic acid, yeah.
We have 1 carbon more than, right? Got it? This is sulfur nucleophiles. This is the same. Instead of O, just imagine S and you'll get it there. Oxygen, sulfur are in the same group. Huh? Sulfur is just below oxygen, right?
Yeah.
Same thing is happening. But this, I want you to notice what is happening in this one. It is called desulfurization. So H2 nickel, it will break this bond and we get an HH. So it's a very nice way where we can convert this ketone into an alkane, right?
Yeah.
Right? Ketone to alkane, right?
Yeah, yeah, sir.
Now reactions of aldehyde and ketone with peroxy acid, we are going to get something which we call, so insertion of an oxygen will occur. So if an aldehyde is there, obviously we'll get a carboxylic acid. This is fairly simple. But in ketone, the problem is whether we get oxygen inserted here or inserted here. See, okay. So which one we'll get? Either the oxygen, if oxygen can be inserted here, then we get the first one. If it is inserted here, then we get the second one. Got it? Got the problem?
Yes, sir, got it.
So, and this is a mechanism. This is a Baeyer vinegar oxidation. It's a name reaction, but you don't need to go much into the mechanism, but you can still see. Now, here is what is important. Migration tendencies studies have been done, and hydrogen is migrated. So if there is hydrogen, the oxygen will be inserted on the hydrogen side, as in this case. Huh? Okay, got it?
Yes, sir, got it.
And now tertiary alkyl has more preference as compared to secondary alkyl. So in this case, and secondary alkyl has more preference than phenyl and primary alkyl and then methyl. So if I have this, so methyl and secondary, so obviously we'll get this, huh? Right? Because this is the secondary one, huh? This methyl group. Huh? Okay? Take a
Uh,
while, take a while.
yeah, yeah, sir.
Okay. Then tell me the products. Try to.
So whichever is better migration, then that will only leave, right?
Yeah, in on that side, it is getting inserted. That is my understanding. Huh?
So in the previous case, like that example they given.
Yeah, the first one will be found. Huh? No, no, second one. Right?
Yeah, okay.
Right.
So in the final product, where is the OR coming from?
In the final product, where is the
OR coming from?
OR?
Yeah.
No, no, forget anything. We know that a peroxy acid is going to supply oxygen. Remember epoxidation for alkenes, right?
Oh, okay, yeah, yeah.
Peroxy acid simply gives O, right?
Yeah.
So here also it is just functioning. Just forget everything. Huh? Here also it will supply oxygen. Now the question is on which side? Huh?
Yeah, okay, whichever is easy to migrate.
Okay, that's it, huh? Okay, got it?
Yeah, got it.
Yeah, so that is why we are going to skip this, what you call mechanism side. Anyways, so we have problem 47, huh?
Yeah.
So which will migrate? So which migrating? So yeah, send me the photographs for this.
Yeah.
Okay. The second one is easy, huh? Whenever there is hydrogen aldehyde, we'll get a carboxylic acid. Huh?
Carboxylic acid, yeah.
In the first one, you have to tell me. On just tell me which side.
So the phenyl side.
Yeah, the phenyl side, and we'll get this ester, huh?
Yeah, and
Okay.
second one is hydrogen side.
This side, huh? Okay.
Yeah.
Okay. Great. Okay, okay. Draw this one, huh? C and D. And send me by drawing, huh? These C and D. Draw and send me. Huh?
Yeah, yeah, sir. So in C, the ring is easier to migrate, right?
I don't know anything. That's why I asked you to send me the photographs. After that, I'll. Regarding that imine thing which you asked, the ammonia, it is relatively unstable. There's the same way imines are relatively unstable, but here is a hydrogen, so yeah, that's what they are saying, that it's not inherently, it depends on the pH stability. Anyways, so that is not a very great consequence. So you can no need to worry about it much. I just checked. They are saying that in some cases we can stabilize it also. But yeah, this is, we are not concerned with this much. Yeah. Yes.
Yeah, sir, done.
Send it and I'll check.
Yes, sir, fine.
Okay. Oh wow, very nice. Yes, we'll get a 6-member ring in this, and we'll get this history. Yes, both are correct. Very good. Okay, the Wittig reaction. This guy also got a Nobel Prize there. This is nice photograph where he was smoking a cigar, but I think they've taken this out in the new edition. Yeah. Anyway, so this reaction appeared only in IIT JEE in once. It was in 1997. So what we do is, see, we use something like pH3, P double bond, and then CR1 R2, you can imagine. And this pH3 P double bond O goes, huh? And we club these and we get an alkene. See, just take a while to see it. I'll also do this. This is going.
Okay, yeah, sir.
Because phosphorus has great affinity for oxygen. Huh? So this takes it, oxygen out. And see how nicely, huh? What a great reaction, see, right? It's almost molecular stitching, right? They stitch these together. It is so, why it is so powerful, and he got a Nobel Prize in 1979. And again, why he's getting a Nobel Prize for this? Because it is a carbon-carbon bond forming reaction, right?
Yeah, yes, I got it.
And I told you that carbon-carbon bond. Again, we don't need the mechanism. We even don't need the reaction. We'll check. I'll check if it is in NCRT. Then we can. The importance of the Wittig reaction is that because if we want an alkene, then we'll have several problems. We'll always get the side products, but the Wittig reaction will not give any side product. Only one alkene is formed. Okay. Here, if we are using hydroxide ion, this proton can also get picked, and this proton can also get picked. So we'll get these two products. Again, here we can get some substitution reaction also, and this product also. So there's a lot of problem in the lab. So this dude solved it, huh? Right?
Yeah,
And this is beta carotene and the C flamingo. The colors are due to these multiple double bonds. So much conjugation, huh? See, right? Double, single, double, single, double,
yeah,
single, double,
yeah,
single,
sir.
double, single, double, single, double, single, double, single, double, single. And how did they prepare it? See, what such a fancy way to prepare, huh? In the lab. This Wittig reaction, huh?
Yeah, yes, sir.
Right? So yeah. This is just too much fatigue. I don't want this much fatigue because it has appeared only. Again, designing a synthesis, the fourth part. You know that this arrow signifies the reverse one, right? And this arrow means that we are before the target molecule, this molecule was there, right?
Yeah,
And this arrow, right? This is a reverse arrow actually, right? And yeah, you can go through this. The same thing which we have been talking about, that we have to think in reverse whenever we are synthesizing anything. Okay, that is what we are talking here. And yeah, you can just go through it. See, there's nothing fancy about it. Yeah. And then you have to do this as a homework using bromocyclohexane. Okay, let's do this. Bromocyclohexane is starting material. How can you synthesize this? So bromocyclohexane. So tell me, how will you synthesize the first one? How will you think about it?
so we can get this from after hydrolyzing.
This is the thing, right?
Yeah,
And I have to make this, right?
yeah,
So how we'll go about this? See how we'll go. Just before this, I think this was an alcohol, and we
alcohol. Yeah,
dehydrated it. Huh?
yeah.
And before that, it was a ketone in which we added grignard,
Okay, yeah, yeah.
right? right?
Yeah.
Now from this to this we have to come, right?
Yeah.
So how do we approach this?
So this ketone will come from um
The first thing is that it must have been an alcohol, right?
alcohol. Yeah. After tautomerizing, it became a ketone.
From bromine. uh, from bromine, how did it? You see, again, we can do a different thing also. Instead of this, what we can do is we can directly add a methyl here. What's it?
So
See,
how?
this is the most powerful reaction,
Oh, okay. Yeah.
right? So I will get this, right?
Yeah. Then we can just put H.
Then we can do this, and we'll get this,
Oh, okay. Yeah. Then just reduce. Yeah.
and then I can do alcoholic OH.
Yeah.
There is one way. Okay, then you also can do the later ones, Okay, try the other things, For example, how can we go about in B? From bromine we are starting, This was A. Now B we are thinking. So B I can make a Grignard, because we have to start from right? Bromocycloid,
Cyclobromine. Yeah.
right? So I make a Grignard,
Yeah. Yeah. Then we get OH group. Yeah.
MgBr, and I add it to which, because it's a primary alcohol, I must add it to formaldehyde, right? Only then I'll get a primary alcohol, right?
Yeah.
Got it?
Yeah, sir. Got it.
C. Oh, COH we have to make. So, oh yes, bromine, Grignard, and CO2,
Okay. Yeah. Yeah, sir. So can we also make Can we also substitute cyanide ion and then just add?
Because cyanide SN2, I won't get very nice result in a secondary alcohol, because it is in between, right? Yeah,
Okay,
technically
yeah.
we can get, but are you getting what I'm saying? The
Yeah, yeah,
fastest
sir.
reaction for SN2 will occur for primary alkyl halides,
Primary
right?
alcohol, yeah.
So we don't want that. Okay, the rest you can do,
Yeah, yes, sir.
See, synthesizing organic compounds now. Now, this is the whole problem, For example, this from yew trees we are getting Taxol, which is very nice in anti-cancer, ovarian cancer, breast cancer, and all those lung cancer. Okay, but the problem is this, that from this tree, 40-foot tree, which may have taken 200 years to grow, it only gives 0.5 gram of the drug. See the problem,
Oh, okay, yeah.
In addition, this Texas forest serves as habitat for the spotted owl, endangered species. This is a Harry Potter.
Yeah.
So, how do we make this molecule? Okay, so in the lab, we make these molecules by see, we start with very simple molecules and then we make this complex molecule. That is the whole art, because you have to control the stereochemistry also, right?
Yeah, yes, sir.
Right. So it will be very challenging, right? And I think this was done by Casey Nicolau, and he may be dead right now, but anyways, I don't think so. So, anyways, we are going to stop till here, and we'll go to some problems. We'll do some problems. Oh, all these reactions are here. I think here we have some problems with the structures, but yeah, do this and send me a 54. 54, don't do G for the moment, for the time being. I'll just write second round, second go. Then we'll do, because we have not done the theory for this alpha beta unsaturated. So yeah. So see, we almost finished everything, right? Much faster than those guys, right?
Yeah, yes, sir.
See, I told you that if we go sequence, and we started with the class 11, right?
Yeah.
We started everything from alkenes, everything. See, sequence helps so much, right? And they are, everybody must be struggling in the class. This I'm so sure of, because alcohols undergo nucleophilic substitution reactions, whereas phenol undergo electrophilic aromatic substitution reactions. Okay, people must not be even knowing it, right?
Yeah.
There will be struggle. There is always struggle with. See, I don't know why they are teaching like this, right? So whom they are teaching like this, right? Why they are teaching like this? Every year I see all the students just imagine, you would also be doing that CBSE, yeah, rule.
Yeah.
CBSE. And then, see, the worst point is then you would start thinking that you are not an intelligent person, right? We start getting, what do you call, negative judgments about ourselves, right?
Yeah.
Our esteem also go down, and we think that, oh, we are not able to. But the fact is that the problem is somewhere else, right? It is not in us, right?
Yeah, yeah, sir.
See, just imagine, and this is happening with so many students every year. There's some students who might try to guide, but they tell me that, yeah, yeah, we want to study from NCRT, and then I, I simply kick them out because because you can read NCRT from anywhere, right?
Yeah.
And you'll never understand it, right? Because in NCRT they'll ask good question, but they have, it's like horrible, horrible. It's like it's like their aim is that you should not understand anything. You should struggle and you should die. It's really horrible. Yes, the subject is so interesting. Everything is so nice. I mean, you can see things, you can predict things, right? That is how it is. I'm trying to look for phenols specifically in the. See, I have also a lot of books, but the sequence is not in every book. For example, there's Solomon Files, whose question we are going to do. So, but I will never suggest a student to start from there because he or she will never understand what is happening. Because the sequence thing is the most important thing. It is not just about, putting reactions at the places and everything. You have to.
Yeah, sir. Done.
Okay, send it. Not- Now you can sit back and enjoy and laugh at your teacher, right? While he's
Yeah.
struggling by teaching it. What he is even trying to do, right?
Yeah, sir.
Phenols he's teaching, huh? These days. What else is going on in physical chemistry? Also, it was going something, right?
Yeah, sir. Yeah. In physical, they just started chemical kind of thing.
Okay, you can ignore that also, huh?
Yeah.
There's no need to. Yeah, yeah, because we'll do in yeah, physical chemistry is super cool. You don't have to do anything. Mm, here's the phenols. It's as if send it.
Yes, sir. Sent it.
Okay, then 55 you can do at home, but I want you to do 58. Okay.
Yeah, sir, done.
Okay, send it. See how things are becoming clear, right?
Yeah.
Anyway, we'll come back to this. Okay. See, in the exams, they will ask you for the product. So you can now see, what is happening here. Just a hemiacetal is getting formed here. No, not a hemiacetal. First OH from here and then the water will go. The two alcohol molecules. One is from the this and one is from the outside. HOCH3, one water will come here, then you turn this
Yeah.
chain around,
Yeah, sir, got it.
and this simply break it, and NH2 will become NH3 plus because the medium is acidic, and this will open as double bond over, right?
Double bond, oh, yeah.
See, now how we are able to predict these danger products. Anyways, we'll continue. Okay. Yeah. We'll continue in the next class. Okay. Take care. Okay. Revise everything.
Yeah, sir.
Okay. Bye.
Thank you, sir.
Bye.